I hope everyone can see my screen, and yeah, I will begin. So in this talk, we'll be covering a bit about binary stars, their classification, and how we can actually find out if a star system is a particular type of binary star system, and how it was sort of useful for discovering exoplanets, which is a pretty important discovery. So let's start by understanding what a binary star system is. And for this, I'd actually like it if you guys can probably put up some suggestions. So what do you guys think a binary star system is? So first, I'd like to hear what you guys think, and then we'll probably dive into what it is. So, I mean, we will
Like
Mhm.
two or more star, like two star system that kind of orbit around each other, having a common center of mass.
Anyone else? Any other answers?
Um,
Yes.
like he told everything, so I don't think there is anything else to say.
Yeah, that's true. Mukund was absolutely spot on with what a binary star system is. So it's basically a system of two stars orbiting around a common center of mass. And a very interesting fact is they actually occupy a little over 50% of the HR diagram. So you have more binary star systems than just single stars, which is good for the population. So one very simple example of a binary star system is Sirius. Might be weird because most of the time when we see Sirius, it's just a single star. But if we can probably zoom in using better telescopes, for example, this image was taken using Hubble. It's quite easy to see that it's got a partner just on its left. So yeah. However, observing this wasn't the easiest of all cases. It took a while, and it was mostly because of just the angular resolution of telescopes, because it had to be improved by optics and other forms of technology. So we were finally able to observe the way Sirius sort of orbits and its other partner, how it might also this dot is not exactly accurate because if you see the previous image, you can notice the difference in luminosity between the two stars. So it's actually very difficult to observe this, uh, even if it's passing in front of Sirius, even if it's a little towards its left, because Sirius is really, really close and really bright. So that's an issue as well. So this is most likely just a numerical extrapolation using a few simple laws like Newton's laws and Kepler's laws. We look into this as well. Um, Again, to just re-emphasize a couple of things, uh, this image that we first saw is completely wrong, by the way. This is a very naive image because it shows that one star is orbiting around another star, similar to how we were at least taught that planets seem to orbit around the sun. Both of those statements are false because, in truth, both of the stars actually just orbit a singular center of mass, uh, and this is generally referred to as the barycenter. That's the technical term that's used. So whenever you think binary stars, you must be thinking of conic sections and center of mass reference frames, which I'm sure everyone must be familiar with, because that's just how the math seems to work out. That's just how they seem to be, and this is not just true for the Kepler's set of laws that we have. It's also true to Einstein's equations, but again, obviously to a certain approximation. This slide I've just kept in just to remind people of ellipses because I totally forgot when I started reading up on this, so I thought I'll remind myself as well. So when you're thinking of an ellipse or when you're thinking of a circle as well, they're just conic sections, and for an ellipse, it's just a special case and it has a few characteristics. So you have the foci in which the objects usually masquerade in, and then you have the semi-minor axis, which is the closest approach, and the semi-major axis, which is the longest approach a star can take from its barycenter. And throughout this talk, we'll label the semi-major axis as A, and for two different stars, we can have A1 and A2, two different semi-major axes, because you can have two different orbits about the same barycenter. And eccentricity is basically a dimensionless ratio, naively put, that characterizes how much of an ellipse something is, or how much of a different conic section. So if your eccentricity is 0, it's a circle, and if it's not 0, it tends to becoming an ellipse. So these simple facts will help us along in the math that we'll cover later on. But before we head to the math, I think it's always good to just look at nature and just observe what's there, and what are the conclusions we can draw from the commonalities that are present. This is usually called phenomenology, and that's exactly what we'll do first. We will first look at how we classify binaries and how do we identify them as well, because obviously there's the visual approach, but there are so many other ways in which we can do so as well. The first one is an optical double. An optical double is actually not a binary star system. It's actually just a illusion, in fact, because when viewed from the Earth, they seem to look like a binary star system, but that's only because their angular separation in the night sky looks pretty close, but they can be very, very farther apart. So this is just an illusion, and it's quite whenever you're looking at constellations, it's quite easy to sort of get into thinking, okay, yeah, these are binary stars, but most of them unfortunately tend to be optical doubles. And the next type would be a visual binary, and obviously Sirius is a visual binary because it is a binary star system, but we can simply just use a a good telescope, even a ground-based one sometimes, to identify the angular separation between them. Obviously, how do you differentiate between a visual binary and an optical binary is the easiest way to do that is to actually use telescopes like Hubble and other X-ray and so on, satellites that we have, to sort of gauge at different planes of different viewpoints their angular separation. So based and sort of observe that over time, and based on that we can conclude if what we saw, if our optical double was just an optical double or was it a visual binary. And there's obviously the other type, which is an astrometric binary, which is the issue with an astrometric binary is there's only one visual member. We really can't observe the its companion due to a couple of reasons. One is obviously due to its magnitude. So if the apparent magnitude of the visual member is very large compared to the companion, it's highly unlikely that we'll spot the companion. So it will just be hidden in its light, absurdly. But sometimes it could just be our viewpoint, the plane at which we are observing it. So we may not actually see the companion. But how do we know that there's a companion? Well, we can just observe the motion of the visual member and see if it fits what we would expect from a binary star system. If you can actually guess a barycenter along which this is moving, then it's probably a binary or it's a black hole. So you have two different options, and based on its path that it takes after close contact, because if it comes in close contact with a black hole, it's either gone or if it's slingshot. But if it's a binary, then you have this nearly smooth kind of oscillatory motion. And as I mentioned earlier, we can sort of use numerical methods, work backwards if you know the barycenter, and guess the unseen companion as well. So these are astrometric binaries. And the other type, very interesting, is the eclipsing binary. And the eclipsing binary is particularly important because it's also relevant to the case of exoplanets, and it's quite close to how it was discovered. So eclipsing basically suggests the motion of one body passing over the other, and that's exactly what happens here. So our the plane at which we view these stars, it's just right through them, so you can actually see one star moving over another star. So this is a plot where we have the apparent magnitude versus orbital phase, which is basically how far along the orbit it is. So this is basically suggesting to us that the star, its companion. So there's obviously this star, which is just bright, and then when its companion star passes over it, there's a decrement in its apparent magnitude, and this is where you can say that the eclipses happen. And based on this, just this plot, which is generally called the light curve, based on the light curve, we can sort of calculate its mass, its surface temperature, based on just a few set of laws that we have. But again, the case with these eclipsing binaries is that there are many subcategories, and each case is very special, very unique, just because of the proximity of the two stars. I'll just explore a little bit onto it because I think it holds relevance. So the first type is the Algol stars, which is just named after the star Algol, in which it was first observed. So what happens here is that obviously there's eclipsing going on, but this is our viewing plane. We're directly able to view it, and another thing is there's a good amount of angular separation between them. So there's no really transfer of dust, or there's no so obviously when you're thinking of a star, you must think of the gravitational potential around it, and due to the gravitational potential, it garners a lot of material around it. It could be dust or planets or asteroids or comets, and due to the angular separation, these material, at least for our cases, we can say that they do not interact, or if they do interact, they don't seem to affect the magnitude we seem to observe. And this is pretty similar to the plot that we had before. So there's a primary dip and there's a secondary dip. So there are these are called minima, and this is called the primary minima. And yeah, so and well, what happens, this is basically due to the again the temperature difference, or the we're just assuming that this star is cooler than the other, so that's why it doesn't exactly cause a increase in brightness per se, even though it passes in front of it. The next type would be the beta Lyrae star. So what's actually happening here is this is a different viewpoint. This isn't exactly viewing at the plane, but and this isn't exactly an orbit. This is actually the gravitational potential of the two stars respectively. And what's happened is the gravitational potential of the smaller star is sort of latched onto the gravitational potential of the larger one. And this latching, this is called a Roche lobe. And due to this latching, what happens is there's a bit of material that's being pulled from the smaller star to the larger one, and it's slowly sort of losing its mass to the larger one. It's sort of like a living star eating a little one. And again, the characteristic is a little different, and again, there are going to be much weirder, much more chaotic features in the light curve, because unlike the previous case where there were obviously you can only have two types of dips, right? Because there's no mass transfer, there's no such wild thing happening. But here, since there's mass transfer, you get a lot of very complicated terms as you progress along the light curve. And the third and final type, which we'll discuss in this subcategory, are these WUMA stars, which basically stand for Ursa Majoris, W Ursa Majoris stars. And what's happened here is that these two stars, both of their gravitational potentials have sort of latched onto one another. There is no real small star or big star, because both are sort of steadily losing their mass to one another. And this actually has a few interesting things. So number one, because there's a lot of infalling material that comes with mass transfer, so your surface temperature will be altered steadily across the lifetime. So you really can't. It's quite difficult to gauge the surface temperature, unlike the previous cases. And there's also a bit of a reflection phenomena where when they're in contact over here, there's a tendency to heat these two sides that are facing it, and thus when we're observing these stars from nearly any particular plane, this lobe portion will be the brightest segment due to the heating and mass transfer that's happening. And again, because of the way we view things, it's quite easy to confuse this with other types. And this is because, uh, well, your stellar disk is actually quite fainter rather than the center. So when if we are not too sharp enough, we might just see this part and not the the characteristic dust around these stars, because this isn't exactly just one circular body anymore. It's got a really weird shape. And there's also another effect where uh, you know along these edges, what happens is, since there's a lot of steady mass transfer here, this is probably the hottest segments of the star, these two portions, along these two portions. Whereas the farther you get away from the center, you have what is called gravity darkening, which is to say that the farther you get away from this portion or this line that might connect these two, the more less energy or light you will mostly radiate. So these are a few weird features, and it's quite easy to get things muddled up. And this is pretty much the state at which these binaries exist. And much interesting, this is probably the most interesting, because what if you're not able to visually discern them at all? What would you do? Well, the obvious next step in astronomy is just spectroscopy. And what happens here is pretty simple, as this diagram can explain. So if you've got two orbits like this along the barycenter, so you're going to see spectral lines, absorption lines that you'll measure from the light that's being produced. But of course, uh, two effects will be dominant here. One is the star that is closest to your vantage point will have its spectral lines will be much more brighter, and also if one of the stars is a few magnitudes brighter than the other one, that's going to dominate the spectra as well. But there's a way to distinguish it, and again, nature provides this way. Uh, the spectra will be shifted due to the apparent motion of the binary that we can observe. So one would move away from us, one would move towards us. Again, there's going to be Doppler shift due to this. And the beautiful part of this is the Doppler shift not only provides quite distinct spectra, because even if one spectra is dominating, your the secondary spectra is going to be Doppler shifted. So at least with respect to the other, so you'll have two different sets of spectra. And this Doppler shift is actually oscillatory. So at this stage, you have star A, which is moving towards us, to be blue shifted, but again, in the other stage, it's red shifted because it's moving away from us. So if you observe your spectra over time, it's quite easy to see this oscillatory motion, and voila, you've found yourself a binary system. So this is pretty much the ways in which it's sort of classified. And now I'll actually hand it over to Samarth to take over how we actually determine the mass and various other things that sort of led us to exoplanets. Thank you.
I thank for setting up all the this beautiful story behind what I'm gonna do now. Am I audible? I'm audible to
Your
everyone?
voice a little break.
You're breaking. Your voice is. You're audible. Wait,
But you're
is it only for me or
breaking.
like other voice is
Now
like
and then.
okay? I'm not robotic now, right? Okay.
Even my voice
Fine.
is breaking. So,
Oh, now it's okay.
It did. Now it's
okay.
fine.
Yeah, is it okay now?
Yeah, yeah. It's
Yeah, yeah.
awesome.
Okay, nice. Yeah, so I will thank Pugal for setting all the previous background and all these stories which I'm gonna build, tell you about these techniques. So these are not nothing great. It's just a simple mathematical techniques based on a simple observation as well as a simple formula. And but they are very informative. They are very informative because we can tell about important properties of these stars such as mass, brightness, even their luminosity, as well as their temperature. We can all just tell all this very important information about the stars just by doing the observation from our telescopes, that is from the Earth. So actually, we all know that in order to find the temperature of any stars, no one used to go to the star and take a thermometer to measure it. It's just a simple technique which you used to follow. So first, we will know how this mass is determined by using a visual binaries. So till now, we all know what are the visual binaries, and before understanding one thing, we should know that this binary system have their own center of mass. And for suppose Google, go to next slide, please. Yeah. So now we know that this binary system will have a center of mass, and we also know the fact that any system which have their own center of mass, it will try to revolve around that center of mass. So when the system is revolving around a center of mass, obviously it will having a certain distance. If it is a circular motion, then it will be the radius. So suppose there are two stars of mass m1 and m1 is separated from the center of mass with distance r1, and there is another star whose mass is m2 and it is separated with distance of r2. So now we know that from our classical mechanics that m1 r1 should be equal to m2 r2 to be system in equilibrium and stable. So if we know that equation m1 r1 is equal to m2 r2, then we can reach first equation, that is m1 by m2 is equal to r2 by r1. So if we know this equation m1 by m2 is equal to r2 by r1, and then we modify something, then we can easily figure out how to measure the masses. Here anyway, we with the technique I'm going to tell you, we can only find the mass ratio, not exact mass. But there are other techniques, though they are complicated, certain amount of complicacy is there. But by using those techniques, you can easily find the individual masses. So what I'm going to do, I'm going to replace m1 by m2 is equal to r2 by r1. I'm going to say it is also equal to a2 by a1. Now, what is A2 and what is A1? As Pugal already talked to you about, as he put introduced one picture of the eclipse. So A2 and A1 is nothing but they are the semi major axis and semi minor axis of the eclipse. So for a normal cases, I'm not talking about the specific cases where the binaries are in a circular motion. There are no such cases, but yeah, over the approximate cases, there are certain binaries which you can find the stars binaries in a circular motion, but in the normal cases, mostly they are in a ellipse. So here my A1 and A2 are nothing but they are the semi-major axis of the eclipse. So these will be two different values. We know that the semi-major axis will have a different value. Now what I am doing, now if the distance from the observer to the binary star system is d, now I'm saying suppose I'm measuring stars whose distance is d and distance d is known, then and the thing is you will question how I can find a distance d. So then you can find a distance v by another method known as a trigonometric parallax. I think everyone is clear with the what is trigonometric parallax. So easily you can find this distance t by using a trigonometric parallax method of particular star. Then the angle subtended by the semi-major axis are alpha 1 a1 by t. So we know that obviously if you are seeing there is a one image at the end. I will explain further with the help of that end, that is in next slide probably. But try to figure it, try to understand this. Suppose if you are observing any star, obviously you are not just below it, you are at a certain angle. So that star will be have a it's that orbit in the orbit with these two binaries are orbiting. There will be a particular plane that is known as a orbit plane, and there is that orbit, the particular plane known as orbit plane, and you are observing below to it at certain distance d, and so you will make a certain angle with that star from the point of observation. So I am saying that the angle which I am making from my point of observation is alpha 1 and alpha 2. So now I can derive we know the fact that angle subtended is equal to radius into you say take a radius into the arc of circle. Here for a small distance, for a very like in a big sphere, this a distance a1 is a somewhat is small. So I'm taking it as kind of a straight line. This is the approximation. So I can say this alpha 1 is equal to a1 by 2 and alpha 2 is equal to a2 by 2. This is nothing, this is coming just from your simple formula that angle subtended r theta is equal to arc length. So here my arc length is equal to a1 and a2. So I'm just getting a simple mathematical formula to reach this. Now what I can do, I can substitute in my equation 1 with the value of this alpha. So what I will find, now I find m1 and m2 is equal to alpha by 2 and alpha by 1. So I hope this is very basic, and if I can measure my angle or my inclination angle with particular star, and the ratio of these two inclination angle will give me the ratio of this mass system. Now, Pugul, can you go to next slide, please? So, but this is the case when we know that angle is subtended, but in general cases we actually don't know how this angle is subtended. So the case is not as easy as I talk. So there are some other complications, and I will talk about these complications in the coming things. So now what happened, even if distance of the star system is not known, in first cases what I take the advantage of the fact that I am able to find the distance of the stars by using a trigonometric parallax. So what if I am not able to find the distance, that due to certain reason I am not able to find that distance by using a trigonometric parallax, then what I will do? So in that cases, if I don't know the distance, then probably I can't found this alpha 1 and alpha 2 very approximately value. So what I will do, I will use the general Kepler's equation, that Kepler's third law general. As you know that most of us have been not studying, have not been came across this formula of Kepler equation, which state that p square is equal to 4 pi square g m1 plus m2 by aq. Here p is square nothing but it's the time period. So period is basically time what you has been in the form of p, and and here a is radius, a is nothing but radius. So this is a general or generic form of the Kepler's law, and by using this Kepler law actually you can find the same thing, mass ratio, and I'm gonna tell you how you're gonna do that. You just now, as of now, you don't go across about what is I and all. I will tell you that in later on. But first try to understand this is a generic form of the Kepler law, and by using this Kepler law we can also find this mass ratio. So this general form of the Kepler law is the sum of masses of the stars provided semi-major axis, that is A, and orbit is a reduced mass system. So we know that there will be reduced mass of the system. When we are talking two masses, they will be reduced mass, and that reduced mass is known as A, and that is basically A1 plus A2. And then you can also find this ratio by M1 and M2 by using this reduced mass concept, which comes from your general this generic form of the Kepler law. However, doing that is a bit tricky and it comes with complications, and that's why mostly we avoid doing it. So what the direct method we follow is, we find the distance of the stars by using a trigonometric parallax, and by using that distance we use the formula m1 by m2 is equal to alpha 1 by alpha 2 to find the this thing, to find the mass ratios. That is more simpler way. And next, what I am talking about, suppose the case now, as I talk initially about the, as I already talked about the fact that there is an orbit plane. So what is the orbit plane? The plane in which these binary stars are orbiting is called a orbit plane. So now what happened, I am taking a three plane. One plane is my observation plane, the plane from which I am making my observation. Another is a sky plane or universal plane, that is the plane which is a flat or that is a perpendicular to my observation plane, and another is a orbit plane. So Pugul, go to next slide, that will be more better to understand because there is an image in next slide. Yeah, this plane. So in this image you can see that there is one circle that is a there is one ellipse that is not dotted, that is a continuous, that is a basically orbit plane. Okay, orbit plane in the sense, in this orbit, in this plane only my stars are the orbiting. And then there is a sky plane which is a below flat, and then there is a perpendicular to the sky plane is my observation plane. Now what happened, it's not necessary that that orbit plane will be exactly perpendicular to my observation plane. So what happened, the stars can be orbiting any preferred plane, we can't limit that. So they will be making kind of angle that is known as I, that is also known as the angle of inclination. This angle of inclination is an angle between the orbit plane and the sky plane, because there will be some angle between this. I hope this picture is very clear. So the down part, what you are seeing, that is basically your sky plane, and the plane in which the eclipse is drawn is known as your orbit plane. And there is certain angle between that is known as, here it is known as a I, that is known as a angle of inclination, which is very clearly shown in this figure. So we have to note that the orbit of both stars are necessarily in the same plane. So here note that they are more than two stars. They can be in binary two stars. So it's not important that those two stars. So it's not important that the other star, like if both stars in the orbit will have the same plane, they can have the same plane, but that again it will lead to the complications. So but as a special case here, we are assuming that orbital plane and the plane of sky intersect along a line parallel to a minor axis, forming a line of node. So but that I'm not going that complicated place. Please remember that all the stars can be like orbit in their own planes. Like suppose if finally there is a two stars, so these two stars can also have their own different orbiting plane. But here I am not talking about that cases. That's why I am going to another thing, that I am assuming all these planes intersect at a particular point that is known as a line of nodes, and that line of node here I am denoting as a I'm audible to everyone.
Yeah, you're
Hello.
audible.
Okay, cool. So this is the point of line of node which you are saying. Line of node is nothing but the plane where all these orbits are getting intersect. Like these all the points are matching. So the observer will not hear what will happen by taking the simplicity, the special case. In this special case, obviously this is a special case because I am assuming that my all the all the stars, all the stars which are in different binary, they are in a plane and they are meeting to with plane of my sky plane. So the observer will not measure by using this. Observer will not actually measure the angle sustained by the semi major alpha 1 and alpha 2, but their projection along this plane. Now there will be some other variation which need to be done if my plane of orbit is not perpendicular to my plane of observation, because in this case, as I told, the observer will not measure the alpha 1 and alpha 2 with the angles which is subtended by, as I told, that alpha 1 and alpha 2 is the projection, or it is the angle which is subtended between the semi major axis and the line of sight of observation. So alpha 1 and alpha 2 are basically angle, as I told initially. So when this plane, orbital plane, is inclined to the our space plane, our observation sky plane, then at that cases the observer is not gonna measure that alpha 1 and alpha 2. What actually the observer is gonna measure, he is gonna measure the projection, like the projection of alpha and alpha 2, and this projection, the value of this projection will be alpha 1 cos I and alpha 2. For alpha 1 the projection will be alpha 1 cos I and alpha 2 cos I. Google, now you can go to the previous slide, please. Yeah. So this is the actually all the thing written in this slide, but I want to just go through and read all the point. So as told, let I be the angle of inclination between the plane of orbit and the plane of sky, known that the orbit and both stars in the system are the same. As I told, that the sky and or orbit are necessarily not to be in the same plane. They can be certain, and if they are in different plane, there will be certain angle of inclination, and that angle I'm denoting as angle of I. So as a special case, assume that the orbital plane and the plane of the sky defined as being perpendicular to line of sight intersects along the parallel line parallel to the major axis, forming a line of node. As I told, what is line of node? Line of node, as I told, different stars, even in the binaries, different stars can have a different planes, but as a special case, I am talking, they are intersecting at a point, and that point is known as a point of node. Sorry, line of nodes. So the observer, now what will happen? The observer will not measure the actual angles of segment by the semi major axis, that is alpha 1 and alpha 2, but instead of the actual angle, he will measure the projection onto the plane of the sky, that is alpha 1 cos I and alpha 2, alpha 1 cos I and alpha 2 cos I. I think there is a bit correction in this diagram. So for both he had go to previous slide. Yeah, here in the third point, it is written that alpha 1 projection is alpha 1 cos I, alpha 2 projection also written as alpha 1 cos I. Plus, please take it note that is not alpha 1 cos I, instead is alpha 2 cos I. So now what happened? So as we know that we are going to measure projections. So already I had introduced this formula that m1 by m2 is equal to alpha 2 by alpha 1. So already this is introduced. Now what I will do, I will substitute the value of alpha 2 and alpha 1, which I am going to measure. So once you put that, you will substitute their projection, that is alpha 2 cos I upon alpha 1 cos I. And once you substitute the projection, you will again get the projected value of alpha 2 by alpha 1. So we can see that this projection effect can make there is no any significant differences from what I said you earlier and what I am saying now. There is no significant differences, and there is no significant differences just because the both have a same terms, that is cos I, which used to get cancelled. So basically, what does it mean? That it means that when you are observing I, what you are actually seeing, you are just seeing the projection of that angle, particular angle. You are seeing projection, and the ratio of that projected angle or the projection of the angle which is being subtended is the ratio of the masses of two binary system. So this is the thing which is very important to understand. We all know that when the thing is making a certain angle, we are not going to see exact value. We are going to see some projected angle. So here in this, we are going to only take the ratio of this projected angle, and by using that projection angle, we can easily find this mass ratio. Pugal, can you move to next slide now? That image one. Yeah. So now what happens again I introduce you what this formula again, this formula that you're seeing, one big formula downside. Basically we have to understand what this is conveying to us. So we know that to evaluate the sum mass properly, like the total mass of the system, now I had given you the ratio. Now if I say what can be the individual mass of each star, so in order to find the individual mass, what we will do, we will go to this way. We will find the sum masses, that is my mass m1 plus m2 of both masses. We will find the sum masses, and by using the sum masses, I can then find the individual masses easily, right? So if I find the value of m1 plus m2, then I can find the total masses. So now how I can find the sum masses of both stars? So we can find the sum masses of both stars by using this formula that is given to you. And in order to understand how this is coming, so again this is a direct implication of this Kepler's formula, the generic formula of Kepler's, and that can be but please understand, in order to apply it, you need to find the angle of inclination very properly. So the question is how you can actually find the angle of inclination. So you can find angle of inclination by that noting the apparent position of the center of mass of the system. The thing is, you can easily figure out where the apparent position of the center of mass of the system, and by noting the what angle is subtended between the center of mass to the stars, and by using that angle, that position method, and by using geometry, you can find this angle of inclination in the system. As you know that the projection of eclipse tilted at an angle I with respect to plane of the sky, it will always result in a different intensity, as I will talk about intensity later on. So once you find this angle of inclination, then you find the sum masses by using this formula. However, this formula exactly from where it's coming, I think it need a bit more derivation, and I'll slowly go for it at the end if there is a time, or I will share the more detailed version of this equation later on the group. So till now, if but we have to understand the idea that by using this equation we can find the sum masses, and what earlier I had told, by using that you can find the mass ratio, and by combining both you can find the individual masses of the stars. So till now this is the way which by using which we can find the masses of stars. But there is another thing also which we need to figure out. So there are other important information like eccentricity of a star, like temperature of the stars. So that all also you can figure out by using the same thing, by using nearly same method. So Pugal, go to next slide, please. So as Pugal already taught you about this, talk about this eclipsing and spectroscopic bandages, and basically with these bandages, it is very easy to find the other details of the stars, other details in the sense like eccentricity, temperature, even luminosity. But this all can be easily found for this particular set of bandages, because all the method which we have developed is more favorable for these bandages. So now whatever we are going to find is mostly what I'm going to talk about is mostly for these eclipsing and spectroscopic bandages. And the reason for that, the observation that if we are observing these kind of boundaries, there is a lot more changes we can see in the light, or the flux intensity which we are receiving, or the even when we are seeing or observing these two types of stars, two types of boundaries, there is a lot things used to happen even on our optical telescope. So because of the advantage of this, we can figure out the fact that they are much more easy to find other details. So for now, whatever I'm gonna find, like its intensity or the temperature, that is mostly because of this. That will be mostly from this eclipsing and spectroscopic boundaries. So Pugal, please go to next slide. So yeah, so now first thing we have to define what is the radial velocity. So there is a one in Pugal. Have you said that GIF? It's not there. I asked you to say one GIF, right? Yeah, you guys please check it out. Can you guide them to where it is actually? Okay, so everyone has seen that GIF. So basically, if you see that GIF, the understanding these two diagram is much more better, like much more easier. Yeah. So everybody had seen that GIF. So now we can understand that why we are getting this form waveform. This waveform is very much I will tell more about this, and I will also tell why eccentricity is zero. So consider any kind of a spectroscopic binary star system for which the spectra of both stars may be seen. So when I talk about this spectroscopic binaries, I'm taking the cases where I can see the spectra of both stars. And since we know that the individual member of systems cannot be resolved, like you know that in a spectroscopy you can't resolve individual stars. Therefore, the technique which used to determine the orientation and eccentricity of orbits of a visual binaries are not applicable. So you can't, yeah. Okay. Just a minute. Is it okay now? Okay. Is it okay now? Okay. So as I was talking that in a spectroscopic binary we can't really resolve the individual stars, right? So the spectra of the combined stars, and with that combined spectra you can't resolve what is the spectrum of one star and another, what is the spectrum of another star. So the technique which we use to determine the orientation and eccentricity of the orbit of visual binaries are not applicable. So we can't actually apply that technique of resolving the spectra and finding all the orientation and eccentricity is not basically applicable, because that whatever spectra I'm getting at my observation point is like combination of both binaries. It a combined result for binary, like one star and both sides combined result. So what became with another solution, that is uh, we know that these binaries they get affected by their radial velocities will be also getting affected. So radial velocity, in the sense the velocity along the radius is the radial velocity. So if v1 is the velocity, as you can see in the image, uh, yeah. So as you can see the image, if V1 is the velocity of a star of mass m1 and V2 is the velocity of a star of mass m2 at some instant, then as you refer to this image, the observed radial velocity cannot exceed to the V1 sine I. As I told that again in this case also there will be this projection, in the sense, as I told, there is certain inclination is there. So because of that inclination, yeah, that velocity will be the component of velocity will be acting, we can see. So that component velocity I'm taking as that will be, if you resolve, that will be sin I, v1 sin I. So if v1 is the velocity of star mass 1 and v2 is the velocity of star mass m2, and at any instant from the start the observed radial velocity cannot exceed its maximum value will be what I am seeing, that the maximum height you are seeing, that is equal to b1 sin I and b2 sin I respectively. So therefore, the actual measured radial velocity depend upon the position of the stars at that instant. So as you can see from the sine wave, the stars as will keep on moving in a circular motion, as you also already see in the GIF, the velocity will be keep on changing. So at any point where you are seeing this stars, actual velocity is most of the dependent upon the position. So if you are seeing the stars at this particular position, suppose that is somewhere bottom to the bottom of the circle, then the velocity will be different. And if you are seeing the stars at the top of the circle, because the velocity is dependent upon the position, as we know that theta is equal to r into d, that is theta is also dependent upon the radius. So that radius and the position plays a very important role, that theta will play an important role. So did I say something wrong? Yeah, I said wrong. So basically what theta is gonna change, your radius is gonna change. Sorry, I made this small mistake. So as you will see from a point, theta is gonna change, and because of the changing theta, there will always change in the velocity. So the actual measured radial velocity depend upon the position of the stars at that particular stand. So if you talk about a special case, that is special cases, if the direction of the motion of stars happen to perpendicular to the line of sight, then the observed radial velocity will be 0. So that is the, because why that has happened, because then angle value I, that value for me is gonna be 0, or that angle I is equal to 0, then the whole observed velocity I'm gonna see that will be 0. So for a solar system having a circular orbit, as you are seeing in this image, the speed of each star will be constant. So speed of the star will be constant, not the velocity. Please don't confuse. So if a solar system, then there is a circular orbit, the speed is gonna constant, and the plane of orbit velocity lies in the line of sight of the observer, that is less, that can be any angle basically. Then the measured radial velocity will produce the sinusoidal velocity curve. And changing the orbit of inclination does not alter any shape or velocity curves. It merely changes the amplitude. So what I actually mean by saying that, if the inclination angle is changing, so suppose as I talked the inclination angle, so if the inclination angle is keep on changing, it will not change the shape, the sinusoidal waveform which are giving. What it will do, it will only this change the amplitude, because amplitude, as I told, the b1 is equal to, like, apparent, the observed v1, or what we are saying, the velocity, the apparent v1 is equal to basically v1 sin I. So here the sin I factor is a, basically it will change only the amplitude. So the angle of inclination doesn't change anything, it just change the amplitude of the sinusoidal waveform which you are observing. So now suppose if you are observing any stars and you are taking all the data of this radial velocity, and if you are finding this sinusoidal waveform, so it means that the object is moving, that the system is moving in a circular motion. And then we can think about the eccentricity of the system, and then the eccentricity will be 0, right? So this is a basically indirect method. So in this indirect method, what you do, you find the radial velocity, and after finding the radial velocity, you plot it as in the form of the graph as it is shown. And after the plotting the graph, if you find a nearly a sinusoidal waveform, then you can say the object is moving in a circular motion. That is not a mostly case, that is a case to understand. But in actually something different used to happen, which I'm going to talk in next slide. So as you can, this is very important to understand how we are getting the idea of eccentricity with the radial velocity, because we know that as very clear from the GIF how the sinusoidal velocities waveform we are getting, And by seeing this kind of graph, we can have idea about the eccentricity of the system. So, and please, I would like to make it clarification that do not confuse with the angle of inclination, that whether the angle of inclination is playing any role in deciding the sinusoidal form. Here, the angle of inclination is only setting the amplitude, because as I told you that the maximum value which can have is that apparent maximum value you can have is v1 sin I, and why you are getting that? Obviously, you can see what is along your line of sight. You can't see what is not in your line of sight. So what is in your line of sight, if you resolve, that will be sine component, not the cos component. So the angle of inclination, what I talk in that image, is just it's just setting your amplitude. It's not something which causing the circular motion. Circular motion is happening because it's nature, because we know that why system goes into circular motion. That is not responsible. It's just setting the amplitude. So please don't confuse. So now, but this is the just case to understand. Actually, this doesn't happen. Something else used to happen in case of stars, which I'm gonna talk in the next slide. So please, so Pukul, can you go the next slide, please? So as you can understand, as I told that this is something, a case when the eccentricity is not is equal to 0. Obviously, if eccentricity of its path is not is equal to 0, obviously then it will not a circle, it will be some of other shape. So now the same kind of waveform, if you draw, same kind of velocity curve you will draw, that apparent velocity curve, what you will getting something like this. So when I'm saying that eccentricity is not equal to 0, so let it be certain value, let it be E. So when the eccentricity E of orbit is not 0, then the observed velocity curve become skewed. Like as we can see that it's kind of deformed, it's kind of skewed, it's kind of you can understand distorted. It's kind of distorted. So we will draw we can make observation about the radial velocity, and when we are making observation about this radial velocity, we are getting this skewed waveform. And the exact shape of this curve also depends strongly on the orientation of the orbit with respect to observer. And even I can say that like if you see that what exactly shape of this of the waveform which you are gonna get is basically depend upon what is the orientation of your that system which you are observing from your angle of, from your the plane from which you are observing. Because what happens, this all observations are done on the basis of the optical telescopes, and this all observation. So sometimes what happens, our if that orientation is not proper, we used to get a lot of misinformation, and because of that we doesn't used to get the exact shape. So idea to understand here, the basic idea which I want to convey you is that basically we can figure out the radial velocity by measuring the observations, and by after plotting this, then after plotting all the velocities and radial velocities which you are getting, then you can get a kind of curve, and from that curve you can have an idea of the eccentricity. Because and we know what is the for some standard things, we know what is the eccentricity, and we also know what kind of curve for the radial velocity we expect. So we have certain standard, like we know what are if the path is eclipse, what should be the eccentricity, and then what kind of curve or what kind of this velocity curve which we expect. So when then we used to do data fitting, like then there is another smart ways by using this. So we used to data fitting, and by other means we used to find the eccentricity for the given curve. I hope you get the idea how actually we work. But again, in reality, many spectroscopic bonding possess nearly a circular orbit, simplifying the analysis of the system somewhat. So that is again good luck to us that most of the boundaries which we had observed, they are mostly circular. They are mostly circular, as even as you we can see in the given example, that is mostly circular in the shape. So when you are getting this distorted or skewed waveforms, then you can do kind of data fitting, or you can understand, compare with other standard values, and then you can have the idea of what is the eccentricity of the system. And why we used to get this circular waveform from our observation? So this mainly occur because the close bodies tend to circularize their orbit due to tidal interaction and time scales that are short compared to lifetime of the stars involved. So what happens, as we know that there are other factors also, like tidal interaction is there. This is one of the important reason why we used to get this most time what observation we used to made is that circular. And another important is that that is a, you can say it is a natural things which has been like, so the lifetime of the stars which we are doing, like the motion of the stars which we are studying is generally very long, and because of that we are getting a very large amount of data. So when you compare this time scale, when the time scale is being compared, you get this mostly circular find, because you know you go for the, you keep on shifting your skills, and because of the continuous shifting skills, you mostly observe this circular data. So this is the way we can have an idea about eccentricity. As I told you, what is the way by which we can have the idea about the mass. So you can understand the fact that how the basic ideas, basic observational skills is giving us a lot more important information about any astronomical object. So another most distinguished property of any star is finding this temperature. So we'll try to understand how we exactly can find temperature. So can you go to next slide, please? So in this slide, as you are observing, is my audio clear to everyone? Um,
Yes, yeah.
yeah. So in this observe is like you can see, like there is a plane of sky, and then there is a orbital plane in which the plane of sky and a plane of orbit in which my two stars, they are, suppose there are two boundaries. I am giving a more generic picture because it is very important to understand the angle of inclination, because that plays an important role in what you are observing, because we know that we can observe and see only those things which lies in our line of sight. If the things are not going to lie in our line of sight, we cannot for finding ratio, I am taking a four things, that is b naught. I am making a certain that light intensity at a b naught, and then primary light primary minimum, what I'm getting at a primary minimum, and then what I'm getting light at the secondary minimum. Then I can set this equation that b naught minus bp, and again b naught minus bs. Bs is a you can talk about this absolute light what I am getting, or you can say b naught is the light at particular observation, that I'm not going to specify what kind it is. It can be anything at any point where you know the value. So the ratio of b naught minus bp and b naught minus bs will be frs between frl, that these two ratios. And then later on, as I already talked, that FRS and FRL is directly proportional to the T power 4. So you can produce, you can change that equation, and you can bring it out that the ratio of this primary light and minimum what you had observed from that will equal to Ts by TL power 4. So the quantity on the left hand side you can figure out, or you can find out by observational values, like you can figure out and observe. As I Pugal already saw you one diagram where you were seeing the primary and secondary minimum. So by using the primary and secondary minimum, you can figure out what is the temperature. So again, understand that we had find the mass, we had find the temperature, we had find the radius, and we had find the eccentricity. by just our observation. So basically, this is a very important thing to understand that experimental, as we know that astronomy is more of observing and data analysis than theoretical background. Please understand, when I talk of astronomy, please don't repeat. Please do not bring cosmology and other thing also. Yeah, astronomy means observational astronomy. What we are talking is very interesting part, and it need a lot of data analysis. So if you do a proper data analysis, what you are getting through your optical telescopes, then you can find these important parameters for any stars like temperature, eccentricity, mass, and radius. Very, by just analyzing a data. But again, analyzing a data is not easy job. It requires a good computing skills. So that is another thing. So that's where we need to understand that in order to have a in order to have a better career in astronomy, like optical astronomy or this observational astronomy, we have to develop a good computational skills. We have to start playing with data, analyzing with different data. So that is again very important to understand. So yeah, I think I have a very less time. So quickly moving to next slide. So Puga, please go to next slide. Yeah. So computer modeling approach. So as I talked that nowadays computer and this data analysis is gonna be very important thing. So that plays a very important role. So now the modern approach to analyzing this data from binary stars system involving computing is that all this modern approach is coming where you do computational modeling, and by using that, by doing that, you can figure out lot of physical parameters that like radii, effective temperature, determine, and you can figure out radii, temperature, eccentricity, and all these parameters, that physical parameters for any stars, you can figure out by doing this mathematical computer modeling. So how that happens basically, so that can happen in any, just I will give you any ideas how that can happen. So we know that gravitational force combined with many other effect of rotation and all of orbital motion, they alter the star shapes, and then any stars will be no longer simply spherical shapes, but they become bit elongated, or they will become distorted. And as we can see that, suppose these are the two stars, and they are these are the two binary stars, and they are orbiting. So once they are crossing, because of the other for take any potential, take any gravitational force, rotational motion, they change. So because of the these stars, they say that what shape, spherical shape, is gonna change, right? It's not just a spherical shape, it's gonna be into different other shapes. So it is kind of distorted, or it kind of different altered spherical shape. So these models, now the what we do, we used to observe the geometry of these things, that how the geometry is changing, and how what is causing this geometry. And by using this, there are softwares, I'll tell you the name of the software actually you can do. So what happened, the model also, this model also have different information about non-uniform motions and non-uniform distribution of the flux across the observed disk in the stars. So we know that the flux coming from binaries will be changing, and it will not uniform, it will like vary a lot. So what happens, the I'm detecting a kind of non. So I'm telling you basically how we are gonna model. So what should be our parameter of modeling, like on the basis of what we are gonna model. So yeah, you wait. Oh, that's again a good thing. So we have only two slides left, right? Okay, just who all is there? Okay, fine. Then we'll try to understand how this modeling is happening. This modeling happens because of this distortion in shapes, and then there is non-uniformity which we observe in the flux and other parameters which we can respond. So we develop a kind of computer algorithm which used to examine different parameters. So that's all I am going to tell about this computer modeling. Uh, Again, I thought of telling you guys that how the software works, but again, that I'm not going to include as of now. So even in the last slide, go to last slide. So this is the discovery of exoplanet. So basically, this all the principles which we have studied. That is the photometry principle of finding the photometry principle by which we found the temperature or the radial velocity, how we find the radial velocity or other methods. All these principles were used to find the extrasolar planets. So basically, what happened? So if any planet is, if there is any planet, obviously it must be revolving around any stars. So when the stars will be revolving around a planet, sorry, when a planet will be revolving around the stars, it gonna cause, it gonna cause all those effects which the stars is causing. Like it will cause dip in the or light which we are observing. It will also eclipse the star from our observation. So with the help of all these tools, we discovered a lot of extrasolar planets. So we discovered a lot of solar planet. I think some other day we'll take a whole session on the extrasolar planet details. But to understand this whole this principle, what the principles which we use for searching the solar planet were from the stars only. They were not something foreign principles. They were just these principles only which we had used to discover the stars solar planet. So I think with all this, I will end my talk. I know it was so lengthy, so and might be complicated too. So yeah,